Good morning, everybody. We are officially on our last unit of probability and statistics. So yay! What we're going to talk about in this unit is another type of inference called a significance test. Basically, this is trying to test a claim about a parameter. So the way I think of it, confidence intervals were take a small sample and let's use that to predict the population parameter. A significance test is more like there's already a population parameter out there and we're kind of trying to disprove it, sort of, is the way I think of it, okay? So a significance test is a formal procedure for using observed data to decide between two competing claims called hypotheses, okay? So basically we're talking about P and then also mu, okay? So if we were together in class, there's an activity that we would do to kind of talk about the reasoning of a significance test. So in this activity, you and your classmates will perform a simulation to test a claim about a population proportion. A basketball player claims to make 80% of the free throws that he attempts. So that is, he claims that P is 0.8, right? Where P is the true proportion of free throws he will make in the long run. We suspect that he's exaggerating. 80% seems high. So suppose the player shoots 50 free throws and makes 32 of them. Well, then his sample proportion is 0.64. This result gives some evidence that the player makes less than 80% of his free throws. But how do we have convincing evidence that that's the case? Other than, like, he could just come back at us, you guys, and say, oh, I just had a bad day. Or, no, the ball is flat. Or, I don't know. We can make up a bunch of excuses, right? So basically, for significance tests, how can we say with confidence that, no, you are exaggerating that you make 80% of your free throws versus, okay, it's possible he did just have a bad afternoon or a bad day, okay? So here's an example where I actually, they used software to kind of simulate 400 sets of these 50 shots, okay? So our set, remember, of 50 shots was he got 0.64, right? So 0.64, looking at the scale, is right about this guy right here, okay? So in 400 sets, only 3 times did they get a p-hat of 0.64 or lower. That's pretty tiny. That means most of the time he's up here, right? Or like if we truly pretend that the 80% is true and we do a bunch of simulations using a computer, only 3 of those random simulations are as low as 64%. So here's what that means. One of 2 things could have happened, okay? Number 1, maybe the player's claim is true. Maybe he does make 80% of his free throws, and just purely by chance, a very unlikely outcome occurred, right? He had a bad day, maybe he didn't sleep very good, whatever it may be. The other option is the player's claim is false, that he does not make 80% of his free throws. He probably makes less than that. So what we need to decide is, okay, how do we know the difference? How do we know, we just got data that is, it's possible that he had a bad day, and how do we say, dude, you're exaggerating, it's not 80% of the time you make a free throw, okay? So what we do is we call them hypotheses, okay? So we state 2 different hypotheses. One is called the null hypothesis, and one is called the alternative. So the null hypothesis is basically what is already claimed, what's already stated out there. The alternative is what we're trying to prove. So in this case, right, we believe that the player might be exaggerating. So our alternative hypothesis is we think that his proportion is less than 80%, versus he's claiming it is 80%. So basically the way we would write that is you would write H sub 0, that's your null, okay, so your null hypothesis, and you would say, well, he's claiming that the proportion of times he makes a free throw is 80%. Our alternative hypothesis, or what we're trying to prove, what we think is the case, is that he's lying, and we think it's less than 80%, okay? The other thing we could say for an alternative, this is considered a one-sided alternative hypothesis. We could actually also say, you know what, I think it's anything other than 80%, making it 2-sided. So what that would look like is that P is anything but 80%, okay? That would be what's called 2-sided. And we'll get into that more as the unit goes on, but it is possible to have the alternative be, no, I think it's anything other than 80%, versus in this case, we're saying, no, I think you're exaggerating, I think it's less. So that's why it's one-sided. So here's a problem. Go ahead and read through it, pause the video, and try to figure out what would be the null hypothesis and what would be the alternative. All right, so in this case, basically what they're saying is the US Census Bureau says that the average household, this form should take 10 minutes to complete, okay? So the null hypothesis is that the mean is 10 minutes, okay? And what we do is we put a little colon there. That's kind of how we notate that. So that's what's already out there. They're saying, the US Census Bureau is saying, 10 minutes. On average, the mean is 10 minutes to take this. We suspect that it takes longer than advised. So our alternative is that we think it's going to take longer than 10 minutes. So just a quick question to think about. Would this be one-sided or two-sided? Well, this would just be one-sided. Okay. If we said that the mean is anything but that 10 minutes, that would be considered a two-sided situation. Okay. So the one that we're working with is one-sided. Okay. So just something to think about. Okay, a couple things as we move forward, okay? The hypothesis should express the hope or suspicion we have before we see the data. So usually what you do is you go out there, you find a statistic that's already out there, and you say, nah, that seems false. I think it's this instead. Then you go and gather a sample, or you gather additional data, okay? I know that for the activity we just talked about where the guy was saying 80% free throws, and we gathered the data first, okay? Usually we do our hypotheses first, and then we go gather data and see if it supports, okay? Also, hypotheses should always refer to the population. So you're never going to use p hat or x bar when writing null and alternative hypothesis, okay? You're always talking about population parameters, big picture here. All right, so there's also this thing called a p-value. So a p-value of a test is the probability of getting evidence for the alternative hypothesis as strong or stronger than the observed evidence. So let me rephrase that a little bit. Here's an example, okay? Here's our null, here's our alternative, okay? What they do is they ask a random sample of 20 teens, okay, to record their food and drink consumption for one day. They end up getting an X bar 1,198. Well, remember, we're thinking that it's less, so already I'm kind of thinking, oh, that's a good sign, all right? What happens is, though, we need to perform this test over and over and over again. We can't go against the National Institute of Health because we surveyed 20 kids and, oh, well, we got different numbers, right? It doesn't work like that. You need to survey more than just 20 kids. So we need to survey 20 teens over and over and over and over and over again to get almost like a dot plot of a lot of data. And what they did was they ended up getting this p-value. It's basically the probability, so we'll talk about that in a second, a p-value of 0.1405. When it says interpret the p-value in context, it means the likelihood of getting the average being 1,198 milligrams is a probability of 0.105, okay? So the likelihood of getting that purely by chance, purely by random, is that probability, okay? So here's how we make a conclusion based on that. If the p-value is small, we reject the null hypothesis. We conclude that there is convincing evidence for the alternative. And I'll talk about what that means a little bit more as we continue, okay? If the p-value is large, we fail to reject the null. Now, here's what's weird about this, you guys. If you are an AP Bio, you can accept the null hypothesis. That is not the case in statistics. So if you're an AP Bio, that might kind of confuse you a little bit. So let me know if I can help, okay? So, for example, let's look down here really quick. In the activity about the free throw shooter, the estimated p-value was 0.0075. So if I were to interpret that, that means the probability that he got only 64% of his free throw shots, purely by chance, purely by, oh, he had a bad day, is a probability of 0.0075. That probability is super, super tiny. So what that means is the likelihood he got it purely by chance is so small that I think we were right, that he does not actually make 80% of his free throws. That's kind of how that works. So, for example, that one problem where we were looking at the p-value, what conclusion would you make? Well, the p-value was 0.1405, or as a percentage, That's 14.05%. Okay, that's actually pretty decent. Like, okay, we got a lower number than what they were claiming, which was 1,300, and the probability we got a lower number was 14%. So it's possible that we got a lower number purely by chance, purely by the particular 20 teens that we talked to that day. So that's not really enough to go against this company and say, you're wrong and it should be smaller. We need a much lower probability for that to happen. Okay, don't forget just this slide, all that I'm talking about here, you can never accept the null. Either you reject the null hypothesis, meaning the alternative is true, or you fail to reject it. Okay, we're not actually confirming anything about the null. We're purely just testing is our alternative plausible. Okay, so if I reject the null, hey, our alternative is plausible. It's possible I'm right. And if I fail to reject, okay, I don't have enough evidence. Maybe I need to go back and try the data again if it's something I care about. Okay, so this unit is very, very conceptual. It's kind of weird talking about this null hypothesis and, well, when the p-value and what's this p-value, and the hard part about this unit, you guys, especially doing this for remote learning, is it's going to take some time, right? It's going to all of a sudden click at some point. But for example, right now, you're probably watching the end of this video going, what in the world is Mrs. Nurse talking about? None of this makes sense. I don't understand how this works. If you're feeling that, it's okay. I'm actually going to have a video coming up for Thursday, and then you're going to have an assignment Thursday that hopefully can clarify some of these ideas, okay? But basically, keep in mind, right, you're taking a statistic from the real world. You're disagreeing with it somehow. That's your alternative. I disagree with that statistic. I think it's bigger. I think it's smaller. I think it's different. You go out, you gather data, and then you decide what's the probability that I got my data purely by chance. And based on that probability number, that lets you know, hey, the null is not really the case. I think I might actually be right. Or you look at that evidence and you go, well, I don't think I have enough evidence to say the null is wrong, so let's move on and try something new, okay? So remember, stop by and see me for office hours if any of this is kind of throwing you off, so I can try to explain it a little bit better, but kind of roll with me. Unit 8 is very weird and very conceptual, but I trust you guys. I feel like you can handle it. Just keep me posted if there are things that I need to re-clarify, okay? All right, I'll talk to you guys tomorrow.